Hello everyone, this is exam prep number 4. The worksheet title here says number 3, but the online version should say number 4. So in this exam prep section, we will be dealing with a couple of topics, one of them being visualization, and the other one being survey and sampling frame. So it will be a slightly lighter worksheet in terms of conceptual load. Now, this worksheet is a little long, but the first question, which is about rating visualization, isn't really a type of question that we ask on the exam because it's too open-ended. So I think the solutions provide you a very good overview of why we don't like these visualizations, and therefore I'm just going to pass the question. I'm going to be talking about question 2, question 3, and question 4 today. All right, so let's start with question 2. Here we're doing kernel density estimation with a triangular kernel. Now I find that suppose that I find the boxcar and Gaussian kernel do not produce good visualizations for my dataset, so I decide to develop a new kind of kernel, and that's called the triangular kernel. So it looks like what we have below. Now, maybe we're not so sure about how to finish the mathematical formulation for it, because as you remember from your discussion worksheet, your kernel should follow some kind of mathematical equation so that you can define where is your kernel and how high is it at each value. Okay, so here's an example of a triangular kernel based on the following formulation. And now the first question we get asked is, what is the value of beta expressed as a function of alpha and or z that makes this legitimate kernel to use in KDE? So remember that if you want to use a kernel for KDE, the area under the kernel's curve must be equal to 1, and this is because the kernel should represent something like a distribution. So area under kernel must be 1. And that's, quite frankly, the only condition other than it must be a sensible kernel that tells you how likely the data point is going to happen. So with that being said, now, what's the area under kernel for this? Well, we know that it's a triangle, right? And we also know that this triangle seems the highest when you can minimize this subtracted term, which the smallest it can be is 0. So for example, T alpha of z comma z is equal to beta minus 1 over alpha squared z minus z, which is equal to beta. And that's the highest point of the triangle. Meanwhile, the lowest point will be when we're at the edge. The lowest will be when we're at the edge of the triangle. And specifically, we know that there's the triangle is going to have a non-zero value for a range of 2 alpha, because the equation for a non-zero value shows that your value is non-zero when the absolute value of x minus z is less than or equal to alpha. So in this case, the base of the triangle is 2 alpha. Therefore, the area of the triangular kernel, stated in alpha and beta, is equal to 1/2 times the base times the height, so 1/2 beta times 2 alpha, which is equal to alpha beta, and that should be equal to 1. Therefore, beta should be equal to 1 over alpha. Okay, so in this case, we get that for the kernel to have an area of curve summed under 1, beta should be equal to 1 over alpha. And that's the key answer to this question. All right, now, second. So match the following plots with the most likely kernel functions of the following options: Gaussian, boxcar, and triangle. Okay, so let's look at it one by one. For A, well, the screen doesn't really show it on high resolution because Windows doesn't know how to make related products, but we do see here that there's some cubic edges here, right? It's like this. So we can reasonably dictate that this is a boxcar thing, because other kernels like triangular or Gaussian should give you something that resembles a peak rather than a bunch of square waves. Okay, but in option B, you see that there's like there's like a curvy pattern of peaks, right? Like this. I don't know why I made that sound effect, but anyways, in that case, you can see that this is very similar to a Gaussian kernel. So this should be a Gaussian. Now, part C gives you something that doesn't look that continuous. In fact, if you look at the peak, it looks like the peak is very sharp. So based on the pattern of the peak, we should say that this is a triangular kernel. And last but not least, the D1 has a bunch of square waves, so we would say that it's the boxcar. Nothing else can really exist and make this pattern. Okay, so these are the labelings. Now let's look at C. Suppose I generate the following KDE plot using the triangular kernel. Is my choice of the bandwidth parameter alpha too large or too small? Well, first of all, let's figure out what alpha is really doing. So we know that the base the value of the alpha decides the base, and particularly the larger alpha becomes, the wider the triangular kernel becomes. And in this case, the lower the height of the triangle. Because you can see that the height here of the triangle is inversely proportional to alpha. So here, we see that each of the kernels seems to be initialized at a very high position, and each of the kernels seems to be taking a very low width. So therefore, we would say that alpha here is too small. And in fact, you can relate this to the case of undersmoothing. If you're in my discussion section, you might have heard of this word before, but undersmoothing means that when you're doing your KDE, things look too spiky, and it's very difficult to interpret off it. Okay, so, and then there are two proofs that we have for this. First is that the height of the kernels seem too high, and that second is the width of the kernel seems too low, making it spiky, thus letting us think that the resulting KDE distribution is undersmooth. So, of course, to resolve this, you can just make alpha a larger value. But you need to be careful to not make it too large, or else it looks like what we show in part D, which is, well, now we're using Gaussian kernels, it looks like, and you can see that the alpha here is too large, such that you're actually getting a distribution that doesn't really represent what the original should look like, which is traced in the black curve. So this is what we call oversmoothing. You're losing too much information because the kernel is too wide, and things are just, like, each kernel just looks something like this, or like this, and when you sum it up, it just looks like the Gaussian thing here. Or not the Gaussian thing here, but like the oversmooth curve here. Let me draw it in a different way. So maybe the kernels would look something like this. And it's too wide, so I'm going to draw it like this. And then you can imagine how many of these curves get stacked together eventually. And then as you see, when you sum everything together, it just looks like this very symmetric and vague curve drawn in the yellow color. Okay. So this is the case of oversmoothing. In this case, your alpha is too large. And because your alpha is too large, you should make it smaller to avoid oversmoothing. And of course, you still have to take care that your alpha is not too small, or else you go back to the situation mentioned in part C. So, usually you need some kind of protocol to decide what is a very good value of alpha for you to rely on. Usually visual inspection is the way. You can just plot 10 different values of alphas at once and compare the 10 plots, see which one is better. Okay, so that's enough of KDE today. Now, TS can't sleep. So, well, factually we can, but this is the problem that we're dealing with. So let's talk about it. To convince someone to get more sleep, Olivia created a data frame called production, shown below. And now we have each row for 31 days in the last month about how many hours they sleep. It looks a little concerning. But, let's say that the subpart A, the researchers would like to visualize the distribution of the sleep column. Which of the following visualizations are appropriate? So here, note that we're visualizing the distribution of the sleep column. So we know we're visualizing a distribution, and that puts scatter plots out. Because scatter plots show the relationship of two variables faintly, rather than giving us a visualization of the distribution. Well, here, the sleep column is actually a quantitative variable, so that also makes bar chart not a probable choice. Bar charts are more so for qualitative variables. And scatterplot doesn't visualize the distribution. So therefore, the final answers are histogram, KDE plot, and violin plot. Okay. A violin plot is very useful in that it is at the same time kind of a box plot plus a KDE plot. It's pretty cool. Okay, now, let me try to show you a little more about visualization. So to help Olivia visualize this data set, write one line of code to create a scatter plot of the two variables with sleep on the horizontal axis and branches on the vertical axis, and the scatter plot should also show a least squares regression line. So this is a very, very particular method call that you want to use for this visualization called lmplot, and it's only available in Seaborn if I remember correctly. Or you can also plot two different plots together using PLT, but that's more tedious, so we use the solution version. SNS.lmplot, which is the particular function we use here. So for this function, you put in the data, which its name for data is called production. X is equal to the column name at the x-axis, so sleep. And y is equal to branches. Okay, and particularly, you also want to put in the variable fitReg is equal to true to get the desired plot. Okay, there's also a PLT version of the solution that's not written within the solution file, but that uses slightly more advanced syntax, so we'll not be talking about it. It's slightly out of scope. Okay, now, sampling. So now we're going to problems that are talking about samplings and more specifically population, surveying frame, and the survey you get and the relationship between them. Okay, so the first sampling question asks us about the census. So for these type of question, it's convenient if you annotate the question. So for example, what I'm going to do now is to demonstrate how to annotate this. So the Japanese government would like to survey its 130 million citizens as part of its census. So this is the population, or like the people of interest. Okay, there are 125 million people currently living in Japan. 120 million of them are Japanese citizens. Somehow the Japanese government can survey all 125 million people currently in Japan, but isn't able to survey anyone else in Japan. So this looks like our sampling frame. For this question, terms like refer to people's citizenship, and we assume there's no dual citizen. So you don't have to worry about someone being called American. It's actually secretly a Japanese. The same case for Indian and other nationalities. Okay, now, first, let us organize the prompt's information, which is exactly what we're trying to do. So what's the population of interest? Well, we just talked about it before. It's 130 million citizens of Japan. Around the world is a optional phrase you can put, but I'll just put 130 million citizens. Okay, but the sampling frame is the 120 million people who are in Japan. Okay, then, now, let's categorize people we will and will not be surveying. So the Prime Minister is among the Japanese citizens and is currently in Japan, if the timing is correct. So A would be a good choice. A Canadian tourist visiting Japan is in Japan, but not a Japanese citizen, or also not secretly a Japanese citizen because there's no dual citizenship considered in this question. So while the person is in the sampling frame, the person is not in a part of the population of interest. Last but not least, a businesswoman who has recently returned to Japan after a 10-year trip. So this is a Japanese citizen who is currently in Japan. Therefore, both sampling frame and the population of interest. Last but not least, a Japanese ambassador at some other country. So this person is not in Japan, but is in the population of interest. And the reason why is because the Japanese ambassador is a Japanese citizen. Okay, so option C. All right, now select all the possible sources of bias and error in this method of surveying. So, first of all, do we have selection bias? Yes, because you see that there are people who are not in the sampling frame but in the interest of population, as well as people who are not in the population but still in the surveying frame. So there's definitely selection bias. Is there a response bias? Yes, more or less for every single survey you encounter, there is some response bias. So this is almost always a yes. Is there a non-response bias? Well, we can go back and check the prompt. everyone that the government surveys responds, according to this line. So it's impossible for someone to not respond according to the rules of the question, and therefore the non-response bias does not exist. Is there a chance error? Well, we survey every single person, and whether a person is out of Japan or not is not really due to chance, so we won't say there's a chance error. So therefore, the only choices we'll select is A and B. Okay, now the last question is about K-pop. So someone is a diehard fan of BTS, and they want to investigate how other groups are doing compared to the group they like. So currently, you want to create a survey to approximately estimate the popularity of BTS among American youth. And then American youth is assigned as an American citizen younger than 25 years old. So this is your population of interest. Okay, now what's your surveying frame? Let's look at subpart A. So you set up tables on campus and hand out paper surveys to passerby. So this is your method of surveying, and it hints at the sampling frame, which is just people who walk by your desk. So left out is your sample may suffer from a significant non-response bias. Yes, that's true, because I can just walk by a desk and not respond to anything. This is just like how club fairs happen at the front of Satter's Gate. So this is definitely true. All right, B. Assuming every individual who walks by responds to the survey, you can safely generalize the sample to the population of interest. Well, not necessarily, right? Because the people on campus don't necessarily represent the entirety of an American youth population. So B is not really right. Okay, C, for this sample, there's no need to worry about response bias. False. Every single sample or every single survey, there is some degree of response bias. So C will not be right. Right. So the only choice is A. Okay, and following the sampling procedure, what is the sampling frame? Well, more precisely, it's just whoever passes by your table, because people who are not from UC Berkeley can still pass by your table as the campus is free to enter. So the correct answer here is D. All right. As an alternative sampling strategy, you decide to include the question on the data 100 midterm instead. Which of the following pieces of terminology apply to the sampling strategy? Okay, so basically, you are putting this survey question on a midterm. So it's more or less a convenience sampling because you're just getting whatever you can. Okay, now, here's the tricky part of the question. So whenever, so here's the tricky question, okay, which the solution will be a little different about. So let's talk about the solution first and talk about how to analyze it. So what the solution says is that this is a simple random sampling because the sample is sampled uniformly at random, where each individual or group of individuals have the same probability of being chosen. And this is because we're assuming that everyone enrolled in this course answers every question of the midterm, so the probability that someone answers the question or is sampled to answer the question within our sampling frame is 100%. So they would say yes to simple random sampling because the sampling frame responds with a uniform probability. And we choose from the sampling frame at a uniform probability of 100%. So this is a slightly trickier description and wordplay with simple random sampling. So by the definition at which we do choose from our sampling frame, which is the data 100 midterm takers, at 100% probability, it's a simple random sampling because we're choosing everyone by a uniform probability, which is just 100%. Okay. And then because it counts as simple random sampling, it can count as a probability sampling. Okay, so what's the argument around this solution? Well, sometimes on the internet, you will see definitions for a simple random sampling saying that the population and the sampling frame has to be the same. So if this layer of definition is applied for this year's lecture, then you cannot say that. So generally, this is not a very well-defined question, and we will not be exhibiting related questions like this on the midterm. But this is a slight wordplay that the solution is trying to use, and generally, these two are not well considered. as a good description of our method. Okay, so hopefully that gives you a sense of why the solution thinks the way it does. All right, so last but not least, let's do some critical thinking. For the sampling procedure in part C, where we just take every single midterm taker, name a group of individuals in the sampling frame, but not in the population of interest. So the population of interest are, once again, American youth, so that's American citizen younger than 25 years old. So we can attack this on multiple degrees. For example, you can take the midterm without being an American citizen, so maybe you're an international student. Or you can take the midterm but not be younger than 25 years old. So you can be a student who is more than 25 years old. Okay, hopefully that finishes up the question.